Hey guys, what's going on? Today I'm here to talk to you about the carbon storage solution, Basalt Carbonation. Let's get right into it. Basalt carbonation is a process where captured carbon is sequestered into underground basalt or similar mafic to ultramafic geology as a method to near permanently store carbon dioxide, taking it out of our atmosphere. Basically, carbon dioxide interacts with the magnesium, iron, and calcium present in high quantities within the basalt, at around 20 to 35%. These are used to form carbonate minerals that bind to the basalt. This in turn stores the injected carbon within the matrix vesicles and fractures of the basalt as a precipitate mineral, likely forming magnesite, siderite, and calcite. A complete chemical reaction can be found here with a really nice diagram found below. Recent research indicates that seeding and precipitation of carbonates can be sped up with a catalyst of sodium or calcium chloride, increasing the effectiveness of the reaction, reducing leakages, thus increasing the proportion of carbon sequestered. Additionally, this will take down the reaction time from up to 10 years in some earlier pilot studies, and then 2 years in the CarbFix project down to only a couple hundred days. Once carbon dioxide is acquired through a direct emission source, such as a power plant or air collection, it is either injected through a bore well as pure gas or is dissolved into a watery solution. This is pumped within the earth roughly 300 to 800 meters underground, commonly to be contained within an impermeable barrier where capillary forces can help to control pressure, temperature, and acidic pH, a salinity of around 3.5%, and other reaction-prone controls. Many studies, including the CarbFix project in southwest Iceland, use a baseline carbon dioxide solution. Within this case, an addition of hydrogen sulfide is dissolved within the water as a means to effectively sequester CO2 through mineralization within the basaltic rock units. This method has been used to small scale in Australia, with research and minor projects succeeding in the concept. However, we have a very long way to go, as if we plan to reduce CO2 emissions to align with the Paris Agreement. 4 megatons of CO2 is only equivalent to 3 days of Australia's total CO2 emissions. On the other hand, looking overseas, this shows us much more promising numbers, especially if we look in the northwestern flanks of China, where their spanning projects can sequester just over 96 gigatons of carbon dioxide through basalt. Although verification is a little bit difficult to acquire, regardless, this should give us hope that we can commit to these same actions if we want to reach our cut of the Paris Agreement. Overall, risks of basalt carbonation are low. However, this risk can be increased by seismicity. Overpressuring rock layers can lead to stress, fractures, and possibly the integrity of the bore well. If something were to go wrong due to an error in structural analysis of the rock, leakages can occur, leading to a discharge of acidic water dissolved in organic carbon as a result of the reaction. This can, and most likely will, contaminate any underground water supply or aquifer present. Thankfully, many of these features can be monitored to an ample extent. It is important to note that the carbon becoming mineralized is a one-way process, and due to the sequestration being isolated underground, storage is highly safe. Verification of CO2 storage can be conducted through various geochemical and structural methods. As the reaction results in the formation of carbonate minerals, we can use this to determine the effectiveness of CO2 sequestration. Changes in the host basalt's temperature, pH, and carbon levels can indicate successful reactions. Magnetic surveys can be used to detect anomalously low readings due to carbonates formation reducing the iron content of the basalt. As an example, to measure the effectiveness of the CarbFix project, dissolved inorganic carbon was plotted against carbon-14 isotopes, finding a 95% mineralization rate, remaining consistent over the whole project's lifespan. Although minimal cost evidence is available, it can be extrapolated. From older pilot studies, cost estimates range from $90 to $900 per ton of CO2. However, in 2019, a study came out indicating that this can be reduced with newer technologies to just over $25 per ton. Most of this cost being energy. This aligns with the budget of the CarbFix project within Iceland. However, their cost was significantly reduced due to their carbon source being the power plant, likely giving them cheap energy. This gives indication that basalt carbonation could become a viable carbon capture method in the right location. Due to basalt carbonation technological developments and the slowly decreasing price that is already nearing the current spot price of CO2, this increases the chance that basalt carbonation could be widely implemented into Australia's CO2 reduction schemes. However, at this current time, large-scale national implementation is going to be unlikely due to high development costs as well as a large proportion of the sequestration cost being energy, which itself isn't entirely renewable yet in Australia. Although current national basalt activity shows minimal results, Australia is blessed with large amounts of favourable geology. This image is taken from the CarbFix website that takes all the basalt or similar mafic to ultramafic units, then extrapolates all the favourable underground geology where the technology can be successfully implemented. Taking a step outwards onto a global scale, this is much more promising, as there is so much available basalt on Earth, especially clustered around the north of Australia, the USA's coast, North Russia, Iceland, and so much more. Anyways, Thank you very much, guys, for listening. I hope you had a very good time and learned a whole heap about basalt carbonation. I'll see you next time.